Imagine the following. You arrive at your first programming interview, nerves running high, and after some small talk, the interviewer drops the first question.
What is the most efficient way to sort a million 32-bit integers?
All right, no need to panic. Let's start by ruling out a few algorithms.
I'm sorry. Maybe.
No. I think
that's not a.
I think the bubble sort would be the wrong way to go.
He's right. Algorithms that run in quadratic time, like bubble sort, selection sort, and insertion sort, just won't cut it for a million numbers. That's why in practice we rely on near linear time algorithms like merge sort and quicksort. But can we go even faster? Actually, yes. We can solve the problem about 7 times faster using a really neat algorithm called Radix sort. Surprisingly, it's also probably the oldest efficient sorting algorithm. It was invented way before the first general computers. We'll even show you the 60-year-old machine that does Radix sort. As always, there's much more to this story that we want to tell, including my favorite hack with floating point numbers. So even if you think you know Radix sort, we think you'll still learn something new. This video was sponsored by 80,000 hours. More about them at the end. One more thing, as we were editing this video, the channel actually hit 100,000 subscribers, so thank you all for subscribing, and we decided to do a little celebratory live stream, so join us for that. Okay, back to the video. So, what is the fastest way to sort a million 32-bit integers? Let's start with a simpler scenario. Sorting a million numbers where each number is between 0 and 9. This might seem like a silly example, but things like this do come up. For example, if you have a list of users and you want to sort it by the month in which they were born. In this setup, the fastest solution is an algorithm called bucket sort. Here's the idea. We create 10 empty buckets, one for each possible digit. Then, we iterate through our input. Every time we see a number k, we drop it into the kth bucket, like this. After we finish reading all the numbers, we just iterate through the buckets from left to right. And that's how we get the final sorted sequence. Here's a simple Python implementation. What's the time complexity? Well, we touch every input number twice. Once to put it in a bucket, and once when we merge the buckets together. We also have to touch each bucket at least once, even if it ends up empty. So, if there are n numbers and d buckets, it takes time linear in both n and d. In our example, the numbers were between 0 and 9, so d was equal to 10, but if we wanted to sort, say, arbitrary 32-bit numbers, we'd need 2 to the 32 buckets. Here's how this translates into practical performance. We ran bucket sort for a million b-bit numbers, meaning we didn't have 10 buckets, but 2 to the b. You can see that for 8-bit and 16-bit numbers, handling the buckets is basically negligible, so the runtime is essentially O of n. Bucket sort is crazy fast in that regime, roughly 15 times faster than quicksort on our machine. But for 32-bit numbers, that we actually care about, bucket sort tanks hard. That's because iterating through all those buckets dominates the cost. And even creating the buckets meant that our C++ implementation needed something like 16 gigs of memory, which is huge. When I look at that table, it looks like we're so close and yet so far from the solution. Clearly, bucket sort is horrible for 32-bit integers, but it's so blazingly fast for 16-bit ones. We could try to split each number into two 16-bit halves, run bucket sort on these halves separately, and then somehow combine the result. And that's pretty much what Radix sort does. Let's see if we can figure out how to make it work. Let's first simplify our problem by imagining we have numbers from 0 to 99 instead of 32-bit integers. Our plan is to run bucket sort twice, one for each digit. The left digit is literally more significant, so let's try sorting by that first. We first create 10 buckets, then we iterate over our numbers and put each number in a bucket based on its left digit. After that's done, we empty the buckets from left to right, merging them back into one sequence. This looks pretty good. We're clearly making some progress. In the output, everything that starts with a 0 is grouped together, then everything that starts with 1, and so on. The issue is that we still need to sort the numbers inside of each group. Unfortunately, that's a bit harder than it looks. For example, let's see what happens if we try sorting each group using a separate bucket sort. The problem is that each of the 10 groups now needs 10 buckets, even if most of them end up empty. So that's 100 buckets in total. And if we push this idea to 32-bit numbers, we would have 2 to the 16 groups, each sorted with 2 to the 16 buckets. So then we're back to the problem of iterating over billions of buckets. So we need a better plan. And the ingenious idea behind Radix sort is that instead of sorting each group afterwards, we sort them beforehand. And if we do that, we'll see that a single bucket sort call is enough. We don't need a separate one for each group. What do I mean by that? Well, bucket sort is a so-called stable sort. That means if several elements have the same value, their order after the sort will be the same as it was originally. Have another look at our bucket sort by the left digit and focus on numbers starting with a 7. They happen to already be sorted in our input. You can see how the order is preserved inside each bucket, so the numbers also end up sorted in the output. But that's really interesting. We were lucky and the group of 7s was already sorted, so it ended up also being sorted on the output. But what if we somehow ensured that this was the case for every group of numbers? What if each group was already in the correct order on the input? Well, then feeding this input into our bucket sort by the left digit would already produce a completely sorted output. Radix sort solves this in the most elegant way possible. It starts by running bucket sort for the less significant digit. That looks like a weird idea at first glance, but look at what happens to numbers starting with the same digit. Let's highlight the 60-somethings here. The 3 numbers end up in totally different buckets, and the output sequence doesn't look much closer to being sorted. But if we look at just our 60-somethings, we see that they are now in the correct relative order. And the same is true for all groups, those starting with 0, 1, 2, and so on, which is exactly what we wanted. So we are now ready to do what we wanted to do in the first place, run this preprocessed sequence through our left-digit bucket sort. Thanks to bucket sort being stable, the numbers in each bucket are in sorted order, and that's why the whole output also ends up being sorted. And that's it. We have an algorithm that can sort 2-digit numbers. It's incredibly fast because it's literally just 2 bucket sorts. First by the less significant digit, then by the more significant one. The only problem is that our algorithm only works for numbers with 2 digits. So what should we do for larger ones? In the case of 3-digit numbers, the 2 bucket sorts don't end up sorting the sequence. However, they ensure that all numbers starting with a 0 are in the correct order, as well as all numbers starting with a 1, 2, and so on. So we just do one more bucket sort for the leftmost digit and we're finished. And if the numbers had even more digits, we could just keep bucket sorting. This makes it an incredibly elegant algorithm, if you ask me. For clarity's sake, we explained Radix sort using numbers in base 10, but the interesting bases are actually much larger. To solve our interview question, for example, it makes sense to choose the base to be 2 to the 16. Why not? Numbers can be written in any base, even if that base is something like 65,000. Algorithmically, we just split our 32-bit number into 2 16-bit parts and interpret those as digits. This way we get a really fast algorithm because we only need to run 2 bucket sorts. Each bucket sort simply iterates over 1,000,000 numbers and then over 2 to the 16 buckets, making it really fast. This graph plots the time to sort n randomly shuffled integers. The first line is quicksort, as implemented in the C++ standard library, and the second line is radix sort with a 16-bit base. Notice that this plot is logarithmic on both axes, which gives it some cool properties. For example, here the lines are more or less fixed vertical distance apart, which means that their runtimes scale in the same way when the input grows larger. Radix sort is always around 7 times faster. Well, except here on the left. What's going on there? Well, remember, radix sort always needs to perform at least 2 to the 16 steps to iterate over the buckets when it does bucket sort. This is a fixed cost that our algorithm always has to pay. So for n smaller than 10,000, it's actually slower than quicksort. We can partially salvage this by using a smaller base. The green line shows the performance of using base 2 to the 8. The algorithm is slower for large inputs because we need 4 bucket sorts, not just 2 of them, but the fixed cost is lower and now it only matters for inputs with less than 100 elements. So the upshot is, for sorting 1,000,000 numbers, radix sort wins by a long shot, but if you're just sorting a few numbers, you should go with quicksort. In conclusion, if you ever run into the guy from the interview, make sure to forward him this video because he might be interested. But let's go back to the good old base 10 radix sort. Although that base is not that fast on current architectures, it does have one advantage. You can implement it without a computer. Tom from our team made a trip to Germany to find out more.
I went to the Technikum 29 Museum near Frankfurt, Germany. Besides an amazing collection of old computers and other machines, we found this sorting machine that implements radix sort in real life. This is a punch card from the 1960s. Before the rise of personal computers, cards like these were used by companies to store all kinds of information, such as spare parts for a car company, dietary preferences of patients in a hospital, and much more. But with this much data, how do you keep it organized? Well, this machine from 1958 can do it. And what's amazing is that it's fully mechanical. No RAM, or CPU, just clever engineering. The machine implements Radix sort in base 10. Let's see how it works on these example punch cards, from 1 to 50. You can notice that each card has 2 holes punched out, each storing a single digit. If you recall, we start by sorting the least significant digit. And go! You can see that all these cards end with 9, all these with 8, and so on. But each group is unsorted. I will stack the cards now and run it again, with the most significant digit. Collect them again, and we're done!
So as you can see, Radix sort is the OG sorting algorithm, and it's also super fast. So it's natural to ask, why is quicksort rather than Radix sort the standard go-to sorting algorithm? One thing is that we've already seen that Radix sort isn't very impressive for small inputs, but the bigger issue is that it only works for positive integers. In contrast, comparison-based sorts like quicksort and merge sort are much more flexible. They don't care if you're sorting integers, floats, strings, or even arbitrary objects. They work by comparing 2 elements at a time. As long as you have a function that can tell you which element is smaller, you're good to go. Radix sort is more picky. It relies on the assumption that we're sorting positive integers. If you want to sort, let's say, floating point numbers, then you can't use Radix sort. Or can you? Yeah, surprisingly, Radix sort works not just for ints, but also for floats, which makes it useful in a lot more scenarios. Here's why. When you look into a computer's memory, you only see a bunch of zeros and ones. It's always up to us, programmers, how we interpret them. Bit strings can be interpreted as a bunch of integers written in binary. In this example, we interpret them as 8-bit integers. But using a different lens, we may interpret the very same bit strings as a bunch of floating point numbers. So let's talk a bit more about floats. When we write down real numbers, we sometimes use scientific notation. In that notation, we first write the sign, then the mantissa, and then the exponent. An old IEEE standard from the 1980s by William Kahan and others defines how to store all this information in a single block of bits. Here are the details for the 8-bit version called minifloat. Usually you would use 32 or 64 bits, but for clarity we're going to use just 8 here. The ideas are the same. First, let's rewrite our number using base 2 scientific notation. Next, we split our 8 bits into blocks of length 1, 4, and 3. The sign gets stored in the first bit. To store the mantissa more efficiently, we'll use the fact that the digit to the left of the separator must always be 1, so we don't have to store it at all. We'll only store the part after the dot. In this example, it's equal to 1/8, which can be written as 0.001 in binary. Finally, we have to store the exponent. We have 4 bits available, so we can store exponents from -7 to +8. But there's a twist. Typically, we store the number 0 using the all-0 bit string. The next bit string is used to represent 1, and so on. But we'll use a different, so-called biased format. In that format, the smallest number, here -7, is represented using all zeros. Up to some special cases like handling infinities, that's all there is to it to the floating point format. The question is, what the hell, William Kahan? Why did you decide to store the exponent before the mantissa, and why this weird biased format? Well, let me show you something. Take 2 8-bit strings. Let's first interpret them as floats. In this case, the first floating point number is smaller than the second one. Now, let's use our integer lens and view the bit strings as integers. Although the new numbers look very different from the original ones, it's still true that the left integer is smaller than the right one. And the float format was designed so that for positive numbers, this is always the case. So Mr. Kahan, he really knew what he was doing. So why is this data storage trick relevant? Well, because if you want to sort n positive floating point numbers, you can run the same algorithm that we used for integers. There is literally 0 computing work to be done. All you need to do is convince your compiler that your floating point array is actually an array of ints, and then run the same algorithm. Frankly, I'm mentioning this hack mostly to stir controversy. You either love it or you hate it, there is nothing in between. So Radix sort works for both integers and floats, but unfortunately there's no similar cute trick for sorting general objects with a comparison function, so Radix sort is still not quite as general as the comparison-based sorts. If there's one thing you should take from this video, it's probably this.
The bubble sort would be the wrong way to go.
Okay, but the second thing is that if you understand your problem well, you can often solve it much faster than you could using the standard approach. And that's not because the people who wrote standard libraries were dumb or anything, they simply had to juggle a lot more constraints. The standard libraries are often very general and support things that you don't actually need, which comes at the cost of speed. There are many more examples that you may have encountered. Take hash tables in C++, an incredibly fast and useful data structure. Yet there are slightly less general hash tables that are 5 times faster than the standard implementation. Or take the data structures used in routers used to handle IP addresses. They implement the map data structure using a so-called Radix tree. Those trees, as the name implies, are quite analogous to Radix sort. They can only store integers, but they're incredibly fast, often 10 times faster on relevant data. And that matters a lot in backbone routers that handle millions of requests per second. So this is the take-home message. Oftentimes, the simplest solution is the best one, but there are problems where performance really matters. Speaking of things that matter, let me tell you about this video's sponsor, 80,000 Hours. They're a non-profit that wants to help you think about your career and do something really useful. They believe, and I agree, that most people don't spend enough time thinking through their career choice. It is tricky. You want a role that you enjoy, that you're good at, pays the bills, and actually helps the world. 80,000 Hours looks at what the best available evidence says about how to plan a career that can deliver on all of these. At the core is the idea that you can achieve a lot of good if you think about it seriously. And they've spent the last 10 years researching high-impact career paths and providing free resources and support. Recently, they've concluded, unsurprisingly, that AI, and especially AI safety, is going to be super important. They're now putting a lot of effort into helping people transition into that area. I personally know several people who made the switch a few years ago and are already doing great AI safety work. If you're interested in what they offer, check out 80,000hours.org/polylog. The link is in the description. I especially like their podcast and the career guide. As I've mentioned, they're a non-profit and everything they do is for free. So that's it from me. Don't forget to like and subscribe and check out the blog post with more details. We want to thank Technicum29 for letting us play with the 60-year-old punch card sorter, especially Roland, who gave us an amazing private tour of the museum. If you're ever around Frankfurt, consider paying them a visit. And as always, thanks to all our patrons, we really appreciate the support. Bye!